All right. Hello, everybody. Okay, so it's casual Sunday. I know you're not watching this on Sunday, but that's what we got going on here. Anyways, today we're going to look at some more solving techniques for you guys to get ready for your end of unit assessment. Okay, so here we go. All right, so today we're going to be looking at solving when you have to square both sides. So far we've done kind of two different techniques, or two different kind of solving ones we've kind of gone over. So the first one is just more of a straightforward when you just have like one trig function there and you just get x by itself, and it kind of works out pretty easy. Another type that we talked about was ones where we have to maybe factor. So if you have something squared, something to the first, and then like a constant, you might have to factor that using like the quadratic factoring techniques. You might also have to take out a greatest common factor and then set each parentheses equal to 0 and solve that way. So that's kind of factoring. And then the third technique is using your Pythagorean identities. So we looked at one before spring break, where you had like a cosine squared and a sine squared, and you had to replace one of them using a Pythagorean identity so that you would have all one trig function. Well, we're going to use that same kind of technique, but now we're not going to have anything that's squared. So we're going to end up having to square both sides in order to use a Pythagorean identity. So this technique is called like squaring both sides. All right, so when would you do this? You would do this anytime you have multiple trig functions and nothing is squared and you think a Pythagorean identity could help. All right, so when would you do this? Really, it's kind of like last resort, right? If you've tried everything else, so factoring doesn't work. All right, so we'll say factoring doesn't work. Come on. So factoring slash normal, I guess we could call it, solving doesn't work, right? You try it and it doesn't really work. All right. And it looks like a Pythagorean identity could be used. Pythagorean. There we go. And it looks like a Pythagorean identity just you don't have anything squared, just not squared, right? So it looks like a Pythagorean identity, just not squared. All right. So that's kind of what we're looking for. So definitely this is, like I said, last resort. So you look at your problem, you try factoring, you try taking out GCF, you try maybe just getting X by itself. If none of those techniques work, and looking at what you have, it looks like a Pythagorean identity, just maybe things aren't squared that you want to be squared. So maybe if you have like sine plus 1 equals cosine. Well, we know that sine squared plus cosine squared equals 1, but your problem, you just don't have anything squared, right? So that's what I mean by it looks like a Pythagorean identity, just things aren't squared. All right. Now, if anything in the entire equation has a square on it, you don't use this technique. All right. This is strictly when things are not squared, but they look like sine and cosine go together with a Pythagorean identity. We also have cosecant and cotangent go together with a Pythagorean identity. And then tangent and secant would go together. So if you have like those trig functions kind of paired up, but then, like I said, nothing is squared, we would use this technique. All right, so this is what we're going to do. So for the technique itself, the first step is to get your different trig functions on separate sides of the equation. All right, so first, get the different trig functions. Wow, my handwriting is looking terrible today. All right, get the different trig functions on separate sides of the equation. Okay, so if you have like a sine plus a cosine, you would want to, like, say equals, I don't know, 0. You would want to move the sine and cosine so that they're on different sides. All right. It doesn't matter where the numbers go. Generally, the main thing is really just to separate the trig functions with an equal sign in between. A general rule of thumb is if there's constants, like just plain numbers, you want to put them all on one side. So it doesn't matter which side they go on, just put them on one side. All right. But like I said, the main thing you want to do is get the trig functions on separate sides of the equation. The next thing you're going to do is you're going to square both sides. And remember, when you square both sides, you're squaring the whole side, not just each individual piece. So you're going to have to make sure that you use your squaring binomial rules, because that's going to come up a lot when you're doing these ones. So square both sides. All right, and then the third step kind of for this technique is, once you have squared both sides, you want to use one of your Pythagorean identities. All right, so step 3, use a Pythagorean identity. Right, that was our whole intention in the first place. Right, it looks like a Pythagorean identity, but it's not squared. So what we want to do is we want to square it, and so then we can use the Pythagorean identities. All right, so that's our technique. Now, one more thing. I'm going to move the 2 examples down some, because I want to write one more little piece. All right, so last thing for these ones, so this is something that's true with all equations, not just trig equations, but all equations. If you square both sides of an equation, when you get down to the final, like your final answer, you always want to check for extraneous solutions. All right, because what happens is when you square both sides, you double the amount of solutions, right? We talk about this, right? X squared versus x. X squared is going to have 2 solutions, whereas plain x is only going to have 1 solution. So when you are squaring the equation, you're doubling the amount of original solutions. So some of your solutions can turn out to be what we call extraneous, just a fancy word for extra or doesn't actually work, right? Because when you plug them back in, they won't, both sides of your equation won't be equal to each other, right? And so that's the last thing. So just last step, check for extraneous solutions. Okay, so what you're going to do is you just take your solutions, you plug it back into the original equation, and you just see if they work. And usually it's pretty quick. Remember, you have calculators that can do that. Just make sure that if your problem is in degrees, that you use degree mode. If your problem is in radians, you use radian mode. Okay, so now we're going to do 2 examples so you guys can see what this looks like. All right, so number 1, let's check this out. So we have negative cotangent equals square root of 2 cosecant plus cotangent, and we're solving this between 0 and 2 pi. So theta is somewhere between 0 and 2 pi. So we want all the solutions that would work for this equation between 0 and 2 pi. We know that there are technically infinitely many solutions to these because it just keeps going around the unit circle, bloop, bloop, bloop. All right, but we're just looking for 0 to 2 pi. So if we look at this, there are some key things to look at. So number 1, nothing is squared originally. All right, everything is to the power of 1. Number 2, if I were to add and get everything on one side, so I'm just going to do this so you guys can see, but this is definitely not what you should do. If you were to add cotangent to both sides, right? So add cotangent to both sides. Because a lot of people try this like as their first step. So we have root 2 cosecant plus 2 cotangent. You can't really do much right here, right? Because you have, you can't take out a greatest common factor because cosecant and cotangent don't have anything in common. It's not squared, so you can't do quadratic factoring. You don't really want to get into like turning these into sines and cosines and combining to make a common denominator. I mean, you can if you wanted to. You might be able to get to an answer, but sometimes that's just messy. So what my advice is going to be is to use this technique. So we're going to first, we're going to separate our two trig functions. We're going to put one on each side of our equation. So I'm just going to move the cotangent. It doesn't really matter. So I'm just going to do this as, I'm going to move the two cotangent to the left-hand side. So we have minus 2 cotangent theta equals square root of 2 cosecant theta. Okay, so I've separated my two trig functions, right? Oh, and another thing to look for, right? So if you think about your identities, cotangent and cosecant, if they were squared, would give us an identity, right? For this one, we have, just to kind of write our identity, right? We know that cotangent squared theta plus 1 equals cosecant squared theta. That's our identity that has cotangent and cosecant. So we're going to be using that. All right, but as you can see, everything is squared and we don't have things that are squared. So first step, square both sides, right? We got everything separate and now we're going to square both sides. All right. So since this is being multiplied like the -2 times cotangent, then we're just going to square each individual piece. Remember, if there's a plus sign in between though, then you have to treat it a little bit differently. And I think that's what we're going to look at in example number 2. But for this one, since it's multiplication on each side of the equation, you can just square each piece. So -2 squared becomes +4. And then cotangent squared becomes cotangent squared equals, all right, square root of 2 squared is just 2, and cosecant squared is cosecant squared. There we go. Okay, so here we are. Now what we want to do is move on to that step 3 where we use a Pythagorean identity. All right, so I just wrote it down, right? Cotangent squared plus 1 equals cosecant squared. So what I'm going to do, because it seems like the easiest option, it's up to you. It doesn't matter which one you replace. You can replace cotangent or cosecant. I'm going to replace cosecant because it seems easier. So right here where I have cosecant squared, I'm going to replace that with cotangent squared theta plus 1. So I'm going to replace this with cotangent squared theta plus 1. So this becomes 4 cotangent squared theta equals 2 parentheses cotangent squared theta plus 1. All right, now I need to distribute my 2. So that's 4 cotangent squared theta equals 2 cotangent squared theta plus 2. Remember, distribute to everything. All right, I'm going to move this down some. There we go. All right. Next, I'm going to just move everything, or move the 2 cotangent squared over to the 4 cotangent squared, right? So subtract. So now we're just at our solving part, right? We have just one trig function. So we're just really solving for theta. So that's going to cancel. 4 minus 2 is 2. So I have 2 cotangent squared theta equals 2. Divide everything by 2. All right, and that leaves me with cotangent squared theta equals 1. All right, now to get rid of the square, just like we normally would, we're going to square root both sides. And remember, when we square root, we have to make sure that we put in there that plus or a minus. When we square root, we put a plus or minus. If there's already a square root in the problem, you don't put a plus or minus. All right, so that becomes cotangent theta equals plus or minus 1. All right, now to get theta by itself, we're going to have to do inverse cotangent to both sides. So theta equals inverse cotangent of plus or minus 1. All right, so now we're going to take our journey around our unit circle and we're trying to figure out everywhere that theta would have a cotangent value of positive or negative 1. And we are in radians, so your answer should be in radians, right? If you look at the interval, it's 0 to 2 pi. That is indicating we want to give our answers in radian value. All right, so if cotangent is positive or negative 1, that means I'm at my 45-degree angles. So it's positive and negative, so it's all of them, right? So we have pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. Now, because we squared both sides, we do want to double check for extraneous solutions to make sure that we don't have anything wrong. So I'm going to check at this stage right before I squared. All right, so that's going to be this step right here. All right, so I'm going to go off onto the side, or I can just do it. Let's do it down below. Let's do it right here. So we have -2 cotangent theta equals √2 cosecant theta. All right, so I'm just going to pop in some values here and see if any of mine are going to be extraneous. Okay, so if I pop in negative, so we'll just start with the first one. All right, so -2 cotangent pi/4 equals √2 cosecant of pi/4. Now, for these ones, really the values aren't going to be different. It's going to be the positive or negative signs, because when you square it, right, you create double answers, right? Because we had that plus or minus 1 that we had to do because we took a square root. So don't worry too much about the values. You're more looking at the positive and the negative signs. I'll kind of walk you through what I mean here. So this side of my equation, I don't really care about like the actual value. This is a negative, right? Because cotangent of pi/4, that's first quadrant, so that's always positive. So cotangent is going to be positive, but then you have the -2 out front, so that's a negative value. Over here, cosecant of pi/4 is positive because pi/4 is in the first quadrant and there's no negative out front, so this is a positive answer. So a negative can never equal a positive. So this answer, pi/4, is extraneous. All right, 3 pi/4. So you could really do this in your head, but we'll kind of, like I said, it's our first one, so we'll just go through it together. Cosecant 3 pi/4. All right, so 3 pi/4 is in the second quadrant. All right, so cotangent is negative in the second quadrant. So you have a -2 times a negative number. So this is going to give us a positive, right? A negative times a negative is positive. All right, over here, cosecant in the second quadrant is going to be positive, and there's a positive number out front times another positive number, so this is positive. So this one works, so 3 pi/4 is good to go. All right, number 3, -2 cotangent of 5 pi/4, is it equal to √2 cosecant of 5 pi/4? All right, so 5 pi/4 is in the third quadrant. All right, so cotangent in the third quadrant is positive. So you have a negative times a positive, so this is going to be negative. Over here, again, in the third quadrant, because that's 5 pi/4 is quadrant 3, cosecant is negative, so a positive √2 times a negative number is going to be a negative. So this one also works. So 5 pi/4 is good. And last but not least, we're going to check 7 pi/4. √2 cosecant 7 pi/4. Okay, so 7 pi/4 is in the fourth quadrant. All right, so here we go. So in the fourth quadrant, cotangent is negative. So you have a negative times a negative, which is a positive. In the fourth quadrant, cosecant is negative. So you have a positive √2 times a negative, which is going to make this negative. So that does not equal. So 7 pi/4 is also extraneous. So both of those are extraneous solutions. Cool. So again, you don't have to like write all of it out, but you definitely should at least kind of go through and check mentally, right? And see if you have any extraneous solutions. Okay, let's do the second one. Here we go. Okay, so our second one here has sines and cosines. So we look at it again. We want to see if we can use any other technique to solve this. And in this case, we can't, right? You could put everything to one side, which I am going to move my cosine over, or the 2 cosine over to be with the 3 cosine. But there's no factoring you can do. Nothing is squared. There's no greatest common factor. You can't use a normal solving technique because you have multiple trig functions. So this one is going to have to use one of those, our new squaring technique. So we're going to start by getting all of our trig functions separate. So I'm going to move the 2 cosine. So I'm just going to add 2 cosine to both sides. All right, so that's going to give me 1 plus sine x equals -1 cosine x. All right, now for those of you that don't know, this Pythagorean identity says that cosine squared plus sine squared equals 1. All right, so what I need to do is I need to get things squared because right now all I have are things to the power of 1. So I'm going to square both sides. Now this is where you need to be careful, and I know some of you are going to make this mistake, but please don't make this mistake. When you are squaring the 1 plus sign, you don't just square each individual piece. They're being added, so you have to square it as a whole thing. This is a binomial squared, so it's 1 plus sign times 1 plus sign. All right, which is going to come out to 1 plus 2 sine x plus sine squared x. Be careful. All right, so that right there is where I see the majority of people making a mistake on this problem. All right, on the other side, it's negative cosine x, -1 cosine x. So we're just going to square it, and that becomes positive cosine squared x, right? When you square -1, it becomes positive. Okay, so at this stage, all right, we've now squared both sides. So we want to use one of our Pythagorean identities, all right? And we want to take a look at this. So we have a sine squared, and a cosine squared. So since we have 2 sines, it's going to be more beneficial for us to replace the cosine squared instead of replacing the sine squared, right? Because then you would still, if you replace sine squared with something with a cosine in it, you would still have a sine and a cosine, which is not ideal, right? We're trying to make this all one trig function. So what we're going to do is we're going to replace cosine squared with 1 minus sine squared. 1 minus sine squared. Scroll to the side a little bit. Okay. All right. So that's what I'm going to do. So I'm just going to rewrite. So 1 plus, oops, 1 plus 2 sine plus sine squared x equals 1 minus sine squared x. Okay, so now I'm going to move everything to one side, and I'm going to start solving for x. So subtract 1 on both sides and add sine squared. All right, the ones end up canceling each other out, and this becomes 2 sine x plus 2 sine squared x equals 0. All right, from here, we are going to use our factoring techniques, right? So we have a sine and a sine squared, and there's 2's out front. So what we're going to do is we're going to GCF, we're going to pull out a greatest common factor of 2 sine. So we're going to pull out 2 sine x, and that's going to leave us with 1 plus sine x equals 0, right? So we GCF, we took out 2 sine. All right, and so we were left with then in parentheses a 1 plus then just a normal sine x. Okay, so from here we're going to take each piece, we're going to equal it to 0, and we're going to solve for x. There we go. All right, so we have 2 sine x equals 0. All right, so divide by 2, it's still 0. All right, now we need to do inverse sine on both sides. So we have x equals inverse sine of 0. All right, so we need to think, when is sine going to be 0? And looking at our interval, this is 0 to 360 degrees. So we do want our answers in degrees. All right, so 0 to 360. Sine is 0 at 0 degrees, 180 degrees, 360 degrees. All right, over on the other one, setting that equal to 0, we have 1 plus sine x equals 0, subtracting 1 from both sides, and then inverse sine. Okay, so now we have, oops, I wrote that on the wrong line. All right, so now we're trying to figure out when is sine going to be -1. Right, so we have inverse sine -1 between 0 and 360. That is going to be 270 degrees. All right, so we want to go up and we want to check to see when we would have any extraneous solutions for this problem. So I'm going to zoom out a little bit because I'm running out of some space here. Okay. All right, so I like to go back to the stage right before I squared stuff to do my checking. So that would be 1 plus sine x has to equal negative cosine x. All right, so I'm just plugging in. So if I plug in 0 degrees, all right, I have 1 plus 0, which is 1, equals -1. So that's not true. So negative 0. 0 doesn't work. All right, 180. So that's going to be 1 plus 0 equals -1. So that's going to work. So 180 works. Check. 360, so that's 1. So if 0 doesn't work, 360 is not going to work, right? We can double check it if you want to. You have 1 plus 0 equals -1, which is not true. So nope, 360 doesn't work. Okay, going over to our other one, 270. So that's going to give us 0 equals -0, which is true. 0 does equal -0. So 270 works. All right, so our